Yeah, out here in the West Coast. Yeah, put it down. They call me Roscoe, by the way, just so you know. California, A-Y-A, where every day is Friday. They call me Young Roscoe, the Philly fanatic. Out in the West Coast, showing up my bad habits. I get the people what they want, keep the party.
Hello and welcome back. In this video, I'll be doing a couple of problems regarding triple integrals. Okay, so let's get started. So the first problem, they give us f of x, y, z equals x plus y. Okay, so we have x plus y, and then the region that they give us to integrate over is z between y and x, and y is between 0 and x is between 0 and 1. Okay, so this is our this is what determines our region W. Okay, so we can consider y being our z1 of xy, and then x is like our z2 of xy. Okay, so we have all of our bounds and our function as well, so we can just plug it in at this point. So we have, actually what I'm going to do is write it this way, kind of broken up in to begin with, just to show you the process again. So we have z bounds going from z1 to z2, right, because z1 is on the bottom, and then we have our f of x, comma y, comma z, dz, and then this is dA, which is like dx, dy, or dy dx. Okay? So here, though, I think it's important to draw out our domain pretty much in any problem. That's what I would recommend. So domain, again, excuse me, domain exists in the xy plane. The region, W, exists in 3D space, but domain is in the xy plane. So the bounds on x and y determine what our domain looks like. So we have x going from 0 to 1 of some sort, right? So x can only stay between here and here. And y is above 0, so it has to be above here, and below x. So that would be the upper bound on y would be characterized by the equation y equals x, right? So it goes from 0 to x. So y equals x looks something like this, right? So this is y equals x. And then these intersect at 1, right? The point 1, 1. And we can always solve for that by, we can always solve for that by setting y equals x to x equals 1. All right? So what we can do from here now is figure out, so our y is the one with the function in it, because x is bounded by constants, just numbers. So what we're going to do is start with the simplest bounds on the outside, so 0 and 1, and that corresponds to dx, okay? And then we have the next least complicated, I guess you could say, so 0 and x, and this describes the bounds for y. And then finally, we have our z1 of xy, which is y, and then z2 of xy at the top, which is x. And then our f of xyz, this is dz, sorry. Those are the bounds on z. And then our f of xyz is x plus y. All right? So this is our integral set up. Okay, so these are all in the right order because when we draw the rainbows and everything like that, all that good stuff, well, let me draw the first one. So here, what this one says is that x's, all x's, because this is like our x rainbow, right? Or x, well now it's not an umbrella because it's not on top, but so it's a bowl, I guess. So this valley, it includes all of the x's inside of it, right? All the bounds where x are, okay, all of the x's that happen to be in the bounds somewhere, they're all inside of this bowl, I guess. Now let's make the y one. So this is the y bowl here. So this is y. And as we can see, all of the bounds for this are inside of it. If we had a y here, that would just be strange, I think. I don't think that's allowed, actually. And at least we don't have any y's out here. That would be bad, okay? So the y's are inside, so that's good. And then these z's, all of the z's, there are no z's, so we don't have to worry about that one. So this arrangement works. So we can get started, basically. All right, so let's look at the inside one first, inside integral. So we're looking at this, and we're integrating with respect to z. So dz, that just means with respect to z. And x and y are being held constant. So this thing in parentheses, we can consider that like a number. Okay, so what we'll get is everything on the outside is normal, stays the same. And then I'm just going to bring this set of parentheses outside of this single integral right here. So we get 1 dz, okay, dy, dx, okay? And then from here, now we can just integrate like normal. So we get, I'll write it up here so I can save some space, 0 to 1, 0 to x, and then we have x plus y times z, as z goes from y up to x, all right? And then we have our dy dx here. All right, so I'll continue this on the next slide. Okay. So then we have 0 to 1, 0 to x, and then our x plus y, which is still in front, and then we have x minus y, right? Because our bounds were y to x, and then our after we integrated, it was z there. Okay, and then we have our dy dx at the end, and now we can simplify on the inside there. 0 to 1, 0 to x, and this turns into an x squared minus y squared, dy dx. All right, and then now we're going to be integrating with respect to y, so we're considering x as a constant. 0 to 1, and then we have x squared times y minus 1 over 3y cubed, okay, as y goes from 0 up to x, and then a dx behind there. All right, so let's plug in the bounds for y, and we'll get x squared times x minus 1 over 3 x to the third. And then when you plug in 0, you just get minus 0. All right, so what this turns out to be is, this is an x cubed, right? This is x cubed minus a 1 over 3 x cubed, and then there's just 0. So this is 0 to 1, 2 over 3 x cubed, okay? And then dx here. So I'm going to bring the fraction outside, and then we'll just integrate like normal on the next step. So then we have 2 over 3, and then we get a 1 over 4 x to the fourth, as x goes from 0 to 1. And now we'll just plug everything in. So I'm going to combine these in the front here. So that turns out to be a 1 over 6 outside. And then on the inside, we get 1 to the fourth minus 0 to the fourth. So our final answer is going to be a 1 over 6. Okay? All right, done with that problem. And now I have one more for you.
In the club, time to make it happen. And all the girlies wanna creep at least one time and see if it's true what all they homegirls be saying about my bloodline. And it ain't nothing like a sunny summer day in the city of LA, living busy, getting paid.